ist gut.
Okay, I think it's time to start. Welcome everybody to this session of QCrypt 2020. It's a pleasure to introduce our fifth invited speaker, Xiaohui Bao, who will talk about quantum repeaters and networks with cold atoms. And he is from the University of Science and Technology of China. Take it away, Xiaohui.
Okay, so thanks for the introduction. So before my talk, I would like to thank the organizers to give me the chance to present in this wonderful conference. Today, I'm going to talk about our progress towards quantum repeater and network with cold atomic ensembles. So as we know, photons are the best carrier of qubit for quantum communication. Most experiments make use of direct transmission of single photons or entangled photons. However, direct transmission suffers from severe losses. For instance, in a 300 kilometer long standard fiber, the loss is around 60 dB, which means that if we send 1 million photons, merely one photon in average can arrive at the destination. More severely, the survival photons are not heralded, which means that you have to destructively detect it to verify the survival. These limitations of direct transmission restrict its application mainly to QKD. So can we efficiently transmit a quantum state over long distance? The answer is quantum teleportation, as we all know. Only when the remote entanglement is ready, we will start the teleportation process. Then the problem is shifted to how can we create remote entanglement in a heralded way? We can make use of atom-photon entanglement. If there are two pairs of atom-photon entanglement, we will place the two atomic qubits in the two ends and set the two photons to the middle for interference and the bare state measurement. If photons are detected, we will know that the two remote atomic qubits are entangled. Thus, the creation of remote entanglement is heralded. This scheme works very well for distances up to several tens kilometers. Well, for longer distance, the success rate drops significantly, similar as direct transmission. A clever way is to split a long-distance link into multiple sublinks. We first create heralded remote entanglement using the previous method in each sublink, and later expand the range of entanglement via entanglement swapping. This is the essential idea of quantum repeater, which was previously proposed by Hans Bregel and others in 1998. Similar ideas can be adopted into a two-dimensional configuration, leading to a scheme of 2D quantum repeater. With these schemes, one can construct very complex quantum networks in other topology. Quantum network will enable a number of significant applications other than QKD, such as distributed quantum computing, and multi-party quantum communication. It may also enable applications beyond quantum information, such as cooperative synchronization of atomic clocks and construction of telescope with ultra-long baseline. There are many different physical systems studied so far for quantum repeater and network, such as defects and rare earth ions in solid state, trapped ions and neutron atoms in high vacuum. In our lab, we make use of laser-cooled atomic samples. From our point of view, this system is advantageous in several aspects, such as efficient interaction with single photons via collective enhancement, simple and stable atomic levels, extensive manipulation techniques. Nevertheless, we have to fight against atom movement and have to accept a large and complicated setup. With an atomic sample, the most convenient way of creating atom photon entanglement is to use the process of spontaneous Raman scattering. By applying an off-resonant red pulse, there is a small chance to get a Raman scattered single photon, together with a collective atomic excitation. The collective excitation can be later retrieved on demand as another single photon in a well-defined mode. This scheme was named as DLCC protocol. By engineering a dual Raman process, we can create entanglement between a photon's polarization and the atomic internal state. By selecting multiple scattering directions, we can create atom photon entanglement in the momentum degree of freedom. Targeting applications in quantum repeater and network, it is crucially important to improve the performances of atom photon entanglement. For instance, the retrieval efficiency and entanglement generation probability needs to be as high as possible, and the storage time needs to be extended to the regime of seconds. As we know, optical cavity is a good solution to enhance atom photon interaction. In 2007, the Voltage group made the first attempt by using a linear cavity. There's one significant drawback in their experiment, since the forward and backward scattered photons cannot be separated, while only the forward mode has a long coherence time. In 2012, we performed the first experiment with a ring cavity and improved the retrieval efficiency to 73% for single excitations. With free atoms, the typical memory lifetime is about 1 millisecond. To further increase the lifetime, it is crucial to confine the atom motion with traps. In our experiment in 2016, we made use of a three-dimensional optical lattice to confine atom motion in all directions, and we used the technique of magic trap to compensate the differential light shift given by the lattice. This is the main result. The initial retrieval efficiency is about 76%, and the 1/E lifetime is about 0.2 seconds. Efficiency decay within 1 millisecond is mainly due to remaining atom diffusion. The decay after 10 milliseconds is mainly due to magnetic gradient and fluctuation. According to our calculation, this is the first experiment that combines long storage time with high retrieval efficiency to the regime that fulfills requirement of a long-distance quantum repeater. In one paper published in Optica in 2016, the authors summarized our major experimental results before our work. The horizontal axis is the storage time, and the vertical axis is memory efficiency. If we add our result, it will be on the top right corner, marked as a red star. It's clear that our result is the best. Very recently, we have made a further progress by engineering two control modes to create entanglement between a single photon's polarization and the collective spatial mode of the atomic ensemble inside the cavity. We use a 3D optical lattice to improve the lifetime as usual. The created atom photon entanglement is tested to violate the barrier inequality after a storage duration of 1 second. While the progress of Raman scattering is intrinsically probabilistic, higher excitation probability means more contribution of high-order events, which will lower down the fidelity of entanglement. Is there a mechanism to inhibit high-order excitations? The answer is yes. In 2001, Lukin and others proposed to use Rydberg blockade in mesoscopic atomic ensemble to implement deterministic operations. Such an approach combines the advantage of deterministic operation from the single particle approach with the advantage of collective enhancement from the ensemble approach. Thus, it may enable a very promising system for quantum repeater and network. There have been many proposals of creating atom photon entanglement with Rydberg atoms. While most of them requires multiple internal states for encoding and many pulses for manipulation and interaction. Instead, we have designed a scheme which is very simple and experimentally easy to realize. We make use of two excitations, one in ground state and the other in Rydberg state. The two excitations have slightly different momentums. While Raman manipulation, the two excitations get mixed each other and entangled in the degree of momentum. One excitation can be later retrieved as a single photon. Thus, atom photon entanglement can be created. The essence of this scheme is to realize Raman manipulation and interference of dual excitations. This is our experimental setup. We first create two ground state collective excitations, one in state S1 and the other in S2. By applying the Raman beam R1 and R2, we can couple the two excitations. Later, the two excitations are retrieved as photons for measurement. This is a result. In the top plot, we merely create a single excitation either in S1 or S2. You can clearly see the Rabi oscillations. When two excitations are prepared, we find that at the position of half pi, the coincidence gets minimized, as shown in the bottom figure, which is a clear signature of Hong-Mandel interference. This is actually the first experiment that demonstrates Hong-Mandel interference for collective atomic excitations. Later, we prepare one ground state excitation and one Rydberg excitation. We make the two excitations be slightly different in momentum. By applying the Raman beam, we entangle the two excitations. The atomic entanglement in the momentum degree are later retrieved as photonic polarization entanglement. This is the result for entanglement generation. The top plot is in the eigenbasis, and the bottom plot is in the superpositional basis. The estimated entanglement fidelity is about 0.9, which is mainly limited by misalignment and noise in the detection channels. The scheme has an intrinsic efficiency of 0.5, which is significantly much better than the traditional DLCZ protocol. With two pairs of such atom photon entanglement, it's straightforward to create remote atom photon entanglement without contribution of high-order events. The overall success probability is 1/8. Albeit the scheme is semi-deterministic, it is already very useful for a quantum repeater. Together with the development of single node performance and capabilities, it is also very important to construct small-scale networks to test the basic functionalities of quantum repeater and network. The main trend in this direction is to increase number of nodes and to extend node separations. So far, most experiments are limited to 2 nodes. The maximum separation distance between 2 nodes is merely 1.3 kilometers, which was achieved by the group of Ronald Hansen in Delft with NV centers in 2015. For these network applications, the most important figure of merit is the overall efficiency for one pair of atom photon entanglement, which includes the preparation efficiency and the verification efficiency. For atomic ensembles with a cavity, the typical overall, or without a cavity, the typical overall efficiency is merely about 4 times 10 to minus 4, corresponding to a 3-pair rate of 1 per 147 hours, which is definitely infeasible for experimental realization. With a cavity, the overall source efficiency can be boosted to about 0.1%, corresponding to a 3-pair rate of 1 per 9 hours, which is still infeasible. To further improve the overall source efficiency, we have made a minor modification of the frequency detuning for the control beams, which enable us to use the ring cavity itself to filter out scattering of the control beams. This technique enables us to remove the external frequency filters. Finally, we get an overall source efficiency of 0.6%, which will produce a 3-pair event every 2.6 minutes. In this table, we make a comparison with other physical systems. We find that the overall source efficiency of our setup ranks second, which is merely smaller than the result with trapped ions in a cavity. With our efficient source of atom photon entanglement, we are now able to perform multi-node experiments. We make use of 3 similar setups, with 2 being in one lab and the third setup in another lab. In each setup, we create a pair of atom photon entanglement. We send the 3 single photons into the middle stage for interference. After the interference, the 3 photons get entangled with the 3 atomic ensembles, resulting in a 6-fold entanglement. By detecting the photons, the 3 atomic ensembles will become entangled. This is actually the first multi-node experiment that can be extended to long distances. To extend the distance of 2-node experiments, there's another problem to solve. The photo wavelength of our setup is 795 nanometers. For this wavelength, the loss rate is very high, around 3.5 dB per kilometer, which allows a maximum 2-node separation of several kilometers. To extend the distance into the regime of several tens kilometers, it is necessary to shift the wavelength into one of the telecom bands. There are several approaches to do quantum frequency conversion, such as 4-wave mixing or DFG. In our experiment, we make use of DFG in a PPLN waveguide. The waveguide was made by Fei Ma and Qiang Zhang. By coupling in a strong pumping beam at 1950 nanometer, the signal photon is gradually converted to 1342 nanometer. At the output of the converter, we make use of a series of filters to eliminate noise due to the pumping beam. The dichroic mirror and the long-pass filter are mainly used to eliminate the remaining pumping beam and its double and triple frequency generation. A narrowband filter of 5 nanometer width with a 5 5 nanometer width is mainly used to eliminate the broadband Raman noise. The internal conversion efficiency of the waveguide is about 70%, while the overall end-to-end efficiency of the conversion module is 33%, which includes coupling inefficiency of single-mode fibers as well. The noise level is about 2.5 kilohertz, which will give a signal-to-noise ratio of larger than 20 in our experiment, which is enough. Since the conversion module merely works for a single polarization, we transform the photonic qubit from polarization to time beam, and the two modes will get converted in sequence. Before talking about the two-node results, I would like to briefly mention the methods of entangling remote memories. In general, there are two types of methods. One method is a two-photon scheme, which detects two photons in the middle, thus suffers the whole channel loss and results in a low entangling rate. The second method is the single photon scheme, which detects a single photon in the middle, thus suffers half the channel loss merely and results in a much higher entangling rate. From the experimental point of view, the single photon scheme is more difficult to implement since it is phase sensitive. We first perform a two-node experiment via two-photon interference. The two quantum memories located in one lab in the east campus of USTC. The two single photons are sent to a remote station in Hefei Software Park. There we perform bare state measurement and photon detection. Fiber distance between the two locations is 11 kilometers. Thus, the fiber distance between the two memories is 22 kilometers. The overall fiber attenuation is about 8 dB. The polarization drifts of the fibers are actively stabilized. This is the final result for the two-node experiment with single photon. Okay, this is the final result for the two-node experiment with two-photon interference. The left panel shows the local result without QFC. We see that the fidelity nearly stays constant if we subtract the accidental coincidences, which are mainly due to the contribution of high-order events. The red panel is the result with field-deployed long fiber, which shows the correlation of coincidence in a superpositional basis. From the visibilities measured, we estimate the entanglement fidelity to be around 0.72, which is actually quite close to the result without QFC and long fiber. Nevertheless, the overall entangling probability per trial is rather low, merely around 10 to minus 6. Next, we implement a two-node experiment via single photon interference. The main difficulty lies in controlling the phase of the single photon interference. This problem is simplified to the logging of two interferometers, one for the write-read control beams and the other for the write-out, read-out single photons. The logging scheme for the two interferometers only works during the atom loading phase. To solve the fast phase fluctuation of the long fiber during entangling trials, we introduce a third interferometer with 1550 nanometers through WDM. The final phase fluctuation achieved at 50 kilometer is around 13.4 degrees. This is the final result of entanglement characterization for single photon interference. We measured the interference of single photons retrieved from the two memories. blue for the result of 10-meter long fiber without QFC, and red for 10 kilometer long fiber, and green for 50 kilometer long fiber. We see that the visibilities for long fibers are obviously lower than the result of short fiber without QFC, which is mainly due to the reduction of signal to noise ratio and the imperfect phase control. We also evaluate the entanglement quality through concurrence. So for the concurrence, if the value is higher than 0, means that entanglement is detected. It's clear that up to 50 kilometers, the two memories are entangled. The entangling probability per trail at 50 kilometers is about 4 times 10 to minus 4. Let's make a brief comparison of the two experiments. It's obvious that the entangling probability of the single photon scheme is much higher, which enables to create one pair of remote entanglement in around 0.65 seconds for 50 kilometers long fiber, which is comparable to the memory lifetime we achieved previously. So the estimated quantum link efficiency is quite close to unity already. Well, there is one drawback of our experiment, that the two memories are within one lab and some control lasers are shared. Therefore, there is still a lot to do to really implement a two-node experiment with a large physical separation. For the two-photon scheme, the extension is straightforward, since it merely requires frequency synchronization of remote lasers. While for the single photon scheme, the extension does not seem to be straightforward. Instead of actively stabilizing the remote phase, we may use a strategy called mirror and trial, since the repetition rate of our experiment is rather low, typically around 200 kilohertz. Before each experimental trial, we can send a classical pulse to compare the remote phases and then apply the red pulse to create single photons afterwards. This scheme will work if the phase do not drift far away within several microseconds. We have got some very preliminary result. The left panel shows drift of phase difference between two independent lasers locked with ultra-stable cavities. Within 2 microseconds, it merely drifts around 5.4 degrees, which is totally acceptable. The right panel shows the phase drift of two fibers. Each has a length of 25 kilometers. The phase fluctuation is much smaller. Within 2 microseconds, the fiber phase merely drifts about 0.3 degrees, which can be safely neglected. Therefore, we think it's totally feasible to extend the physical separation of the two nodes to several tens kilometers. Moment in terms of retrieval efficiency, lifetime, and entanglement generation efficiency for our Rydberg blockade. We have also realized a 3-node quantum network and extend the distance of 2-node experiments up to 50 kilometers in fiber. In the near future, we will improve the performance of our Rydberg-based antiphoton entanglement and perform multi-node experiments with Rydberg ensembles. Besides, we will also plan to implement entanglement swiping via Rydberg gates and extend the physical separation of the 2-node experiments. Okay, So finally, I would like to thank you for your attention. Besides, I would like also to thank my colleagues and the students for their contributions. Okay, thank you.
Thank you very much, Xiaohui, for this nice talk. Now it's time for questions. For now, I don't see any questions in the Q&A. If any attendees have questions, please post them there. Maybe in the meanwhile, I can ask a question. So you said that for now in the two-node experiment, the two entangled nodes are in the same lab and they share some control lasers. So maybe can you elaborate how exactly this what correlations between these two nodes are introduced by sharing these control lasers?
So how to say? Actually, so by sharing lasers between the two setups, so how to say, just with one laser for two setups, so the how to say, the control beams will have a common phase. So then it requires no effort to make the phase synchronization. So in the case of long distance experiments, so we have to use independent lasers. So therefore, so then how to say, we need to get the phase synchronization between remote lasers, which is very similar as the TF-QKD experiments.
Okay, thanks.
Welcome.
Well, are there any other questions from the audience? If not, maybe I can ask another question. So at some point in the beginning, you mentioned that you use the ring cavity both for enhancing this Raman scattering, but then also for some filtering. So I didn't understand what exactly you're filtering out and how.
Okay, so I will make brief how to say explanation. Just switch to the slides. Okay, so here how to say the left scheme is our previous scheme. So you see that the how to say, by applying the red beam, so there will be a Raman scattered red out photon. So the frequency are different, but at the same time there will be how to say scattering in the same frequency due to how to say due to for instance the reflection of the windows. Yeah, so the red pulse itself will give rise a lot of noise. So therefore we have to apply a filter, which is a frequency filter which has the same frequency as the red out photon.
Right.
Yeah. So in the new scheme, which is shown in the right, so how to say? So you see that the how to say? Just let me think along. So how to say? You know that our cavity has to be configured to be resident with the write out and read out photons.
Right.
Therefore, for our previous scheme, the cavity is also resonant with the write and read control beams. Therefore, there is no filtering mechanism for the write and read beams. So that is why we have to add external filters to filter out the leakage of write and read. So in our new scheme, the cavity is only will not be resonant with either the write or the read. So then the scattering itself will not be possible to exist in the cavity. So then the ring cavity acts as a filter itself.
Thanks a lot. That was very clear. So basically using these two different detunings, I can see that then you can basically choose your cavity such that it filters automatically the write and read pulses. Now we have some questions from the audience. So Sidhu, maybe you can start. I think you're being unmuted. Okay. Or you can unmute. Can I unmute you? I think so. Sorry, how do you do this? Okay. Sorry, apparently I cannot unmute you. Okay, I can also ask you a question. So Sidhu's question is, what are the major problems in atomic ensembles compared to other platforms like NV centers, quantum dots, etc., in realizing a quantum repeater?
Okay, so from my point of view, each system has its strengths and weakness. For the atomic ensemble system, I think I've talked a lot about the advantages. So there is, one advantage of other systems like NV centers, in the NV centers, they have, but we do not have. For instance, in the NV centers, in each node, they have multi-qubit capability. So around one NV center, there are several nucleon spins which can be used as register. But for atomic ensemble, so it's difficult to have several qubits for one node. Yeah, this is one drawback of our system.
Thanks. I think the next question was by Roelof Schoenmaker. Can you ask it yourself?
Yeah, that's good. Thank you first of all for the talk, but I might have missed it. But in a comparison between TPI, SPI, and NV, the assumed memory lifetime seems to be lower than the work from the NV. Would that be one of the improvements for further work? So I noticed it was 0.22 instead of 0.6 for NV.
Okay, just a minute. I will switch to the slide. Okay, so here, you mean that the lifetime of atomic ensemble is shorter than NV centers, right?
Yeah, from the, so it's slightly shorter, yeah.
I understand your question. Yeah, I think there are, there are several methods we can try in the near future. Yeah, currently as I said, the magnetic field is one of the main limitations. And also another limitation would be the vacuum is a vacuum level. Actually, the collisions due to the background gas is also another mechanism to limit the lifetime of our memory. I think by trying all these possibilities, it may be possible in the near future to extend the lifetime to the regime of several tens seconds. But this will be the ultimate limit. Yeah. It's not feasible to see longer than that.
Okay. Thank you very much.
But for a lifetime of several seconds, we can already do a lot of things. Yeah.
Mhm.
Okay.
Thank you. There's one more question from the audience by Mohsen Razavi. Mohsen, can you ask your question?
Okay, I think I see his question. Yeah.
Chris, you're unmuted. You're muted.
Sorry, I was muted. Yeah, it's a follow-up question. It's just also for the video stream. So the question is why the fidelities in this work are rather low compared to the NV case.
Oh, okay. I see the question. So how to say? Since we performed 2 experiments, the situation is slightly different. For the 2-photon interference scheme, since the entangling probability is low,
Xiaohui, I think we lost you.
reasonable duration. So that fidelity is mainly limited due to the high order events since we increase the excitation rate. So in principle, if we reduce the excitation probability, the fidelity will increase significantly. For the case of single photon interference, so the problem of high order excitation applies simultaneously, but not as severe as the 2-photon interference scheme, since the excitation probability used is lower than the 2-photon scheme. In addition, for the single photon interference scheme, so there are other issues which contribute to the reduction of the fidelity, such as the imperfect phase locking, and also the reduction of signal to noise ratio.
Okay. So yeah, Mohsen, if you heard that, you can.
Yes, thank you. I got disconnected, I guess, in the middle of this discussion. So I understand that the 2 key reasons are phase stability and also the excitation probability that you use. Is it correct that the excitation probability that you have used is on the order of 1% or so?
Yes, around 1%.
So that wouldn't justify the drop of like 30% in fidelity. So is it correct to assume that the reason that the fidelity is on the order of 70% is mainly because of the phase issue?
The 70% is for the two-photon scheme. Yeah. For the two-photon scheme, the main contribution would be the high-order events. Yeah.
So is the fidelity better for the single photon scheme?
For the single photon scheme, we use another figure of merit called the concurrence to measure the quality of entanglement. Since for the single photon scheme, it's not so easy to define a fidelity. So they are just different figures of merit.
I see. Thank you very much.
Okay. Thanks a lot. I think we're out of time for now. So let's thank Xiaohui again for this nice talk, and then we can take all other questions to the meet and greet area. Thanks a lot for coming.
Shall we start? Okay. Good morning, good afternoon, and good evening. Welcome to the business meeting of QCrypt 2020. This is a tradition for QCrypt to have the business meeting for the steering committee, the PC committee, local chair, next chair to report their work. And then, first of all, I would like to thank all of you to attend this business meeting and also the whole meeting during such a hard condition, such a hard time. And I especially thank the local organizer, Christine, Serge, you guys really did a very good job, amazing job to make this one happen. And thank you for that. Okay. I'll see the agenda for today. First of all, I'm Qiang Zhang, the steering committee chair. Together with my co-chair, Serge Faher, I will talk about the summary of the steering committee activities for 5 minutes. And then the PC chair, Fry, will talk about the PC work. And then the local chair and the future chair. Today, this year, same from Amsterdam, Chris and Serge, they will talk about the participants' statistics and then the preview of the QCrypt 2021. And we have 15 minutes for open discussion. And by the end of the talk, we will have the award ceremony. Okay, so from the QCrypt 2019, from last actually September, the steering committee, here you can see the members and you can share our photos on the QCrypt 2020 website. We have Gorjan Alajek from University of Maryland, Marcus Curti from University of Vigo, Serge Faher from CWI, Stacy Jeffrey from CWI, Christophe Marquette from MPI for the Science of Light, Akihisa Tomita from Hokkaido University, Hugo Zibiden from University of Geneva, and me, Qiang Zhang from USTC. This year, we have a rule that 2 members of the steering committee will leave, and we have 2 new members. And this year, Marcos and I will leave the steering committee. So let's see what we have done for the past years. We have 5 meetings since October 19. And then the last meeting is actually last Tuesday. We have 1 meeting per 2 months, something like that. We evaluated the exit survey of QCrypt 2019, basically to define to see how we upgrade our QCrypt conference. We appointed the programming committee chair, Frederick Dupis, and the co-chair Feihu Xu. Both of them did a very good job. And by December 2019, we selected the tutorial and invited speakers, and then we sent the invitation. And then fortunately, all the speakers can give their talk. And then, but by the May of 2020, together with local chair, we decided that we changed the QCrypt to online meeting due to the coronavirus 19 condition. And then we decided Amsterdam will host the QCrypt 2021. And then yesterday we discussed the new PC chair, new IC member, and transition to next year. It's the basic thing. And see what we have done for the past year. We changed the part of the code of the conduct. We basically the main change will be committed. It's a kind of the main, I think the main change is harassment-free conference experience. So if you have some feel some harassment, you have the liaison person like Anne Brabant, Eleni Diamanti, and Ivan Damgard. That's our liaison person. You can find their information in the website. Their contact in the website of the QCrypt 2020. Okay. And also for the online conference, we add one rule is like every participant in the online conference represent themselves by the full name, and they are used for professional work. So that this is our COC. And for the student paper prize, we changed the rule a bit. Here we emphasize that for the best student paper award, submission may still be considered eligible, even if it's not presented by the student. Such exception must be approved by the PC chair before the start of the conference. But sometimes we know the students, because of the visa issue or some family reason, they couldn't show up, but we can still accept that. But it must be approved by the PC chair. And then how can we elect the student paper prize? Later we will show. It's the PC may select a number of eligible submissions for shortlist, and they will vote first. And then the final decision will be made in discussion with the SC, and then the prize will be announced and awarded by the end of the conference. Okay, here is our new steering committee. Gorjan Alajak, Serge Farher, Stacy Jeffrey, Christophe Marquet, Akihisa Tomita, Hugo Zevinen. Except for Qiang Zhang and Marcos left. So, and we elect Christophe will be the chair, and Gorjan will be the co-chair. There will be 2 new members later. And then we still call for the host proposal to QCrypt 2022. And you should send email to Christophe Marquet and the new SC chair. If you are interested, there is a 2-step process. You send a letter of intent to QCrypt, to this QCrypt SC group email list by November 1st, 2020 with the following information. And then the second step is the steering committee will ask the top contenders to work out the full proposal. And then in general, we prefer for the 2020, because 2021 is in Europe, in Amsterdam. So in general, we have Europe, Asia Pacific, and then North America. So for 2022, we prefer Asia or Pacific, but of course it's not limited, but we prefer. And the survey, and there will be, the last information for me is like after the QCrypt 2020, there will be a survey, exit survey, we will take care by Gorjan Alajak. So participants, you are encouraged to take part in the survey and give their feedback. And details, you will find it on the web page and by email. Thank you. Now we'll hand it to the PC chair, Fried.
Thank you, Jiang. I will just share my screen here. Wait a minute. Is that it? It's not showing up. Wait a second. There we go. Okay. Yeah, so I'm Frédéric Dupuis, PC chair for this edition of the conference. And so here you can see the full list of the program committee. So if you're wondering who did all of the reviewing of the contributed talks and selected the final list of contributed talks, This is the list of people who are responsible for this. I'd like to thank everyone who was here. So, and special thanks, especially to my co-chair, Fei-Hu Xu, who handled mostly the experimental talk. So basically, roughly half the PC is composed of theorists and roughly half of experimentalists, so that we could evaluate all of the submissions well. Some statistics about what happened this year. We had 99 talk submissions for contributed talks. If you want to compare this to the last 2 years, we had 95 in 2019 and 102 in 2018. And this year we had 69 submissions that you could classify as theoretical theory submissions, 33 experimental. I think this doesn't quite add up to 99 because some of them were counted in both somehow. And this compares to a split of roughly 75% theory, 25% theory in 2019, and roughly 50-50 2 years ago. So in this sense, you could say that this year was a pretty typical year, and maybe surprisingly normal considering under the circumstances. As far as the acceptance rate goes, we had 33 accepted papers, including 3 mergers. So we had 30 contributed talks in total, and we went for half theory and half experiment in the final program. For posters, in the end, we had 91 posters in total, including 37 poster-only submissions, the rest being submissions that were submitted as talks. And this is much less typical for QCrypt. Usually there are far more poster-only submissions that come up after the deadline. Usually there's something like 100, now we only had 37. So this time there was a big drop, actually. What else? Yeah, so as you can see and probably recall, the deadline was really in the middle of the COVID action. So 1st of April is roughly 2 weeks after the pandemic really went global. So at that time, things were a bit chaotic. And as part of this chaos, we decided to push back the deadline to April 17 to give people some time to get organized. And then the reviewing process took roughly 1 month of reviewing and 3 weeks of discussion. And really at the beginning of this, things were really still up in the air. We started reviewing, not really knowing what would happen to the conference. I think there was still talk of, is it going to happen physically? Is it going to be online? So I'd like to thank everyone who stuck with it and started reviewing under uncertainty like this. One novelty this year compared to previous year is the change from EasyChair to HotCRP. So this is the software package that's used to manage all of the submissions and the reviewing process. So I think if I'm not mistaken, all previous editions of QCrypt used EasyChair. And this year I decided to switch to HotCRP after. So the first thing I did when I took up this job of PC chair was to read a blog post by Thomas Vidic, who blogged about his experience with chairing QCrypt a few years ago. And one of his regrets apparently was using EasyChair, because that's what we always do, and was recommending. It looked to him that HotCRP was a better choice, so I went with it, and I didn't regret it. So I would recommend this to my successors as well. One last point is the student paper award. So the way this was selected is by, so we did a vote among the PC last week to come up with a short list of papers, so to be nominated for the award, and then the final decision was made by the steering committee. And we decided to have one theory prize and one experimental prize. And the result is coming up, so stay tuned. You'll find out very soon who it is. And yeah, that's all I had to say. Thank you. All
right. I guess if there are any questions right now, then I guess there's also time to take those in general. So I guess the usual thing, Q&A, or you can also raise your hand and just let us know. Otherwise, I will continue for now. I hope you can see that. At least it's coming up. Yeah, you can see my screen. Okay. So number of registrations, Serge already talked about it. It just kept increasing. We're now at more than 1,000 people who just filled out this online form. It doesn't mean that they're physically here. We'll see some numbers after that, but here I also plotted a graph of registrations over time. And yeah, so even during the conference, maybe people forgot their access or so, but they kept coming, and I think they still keep coming. So we keep sending out registration participation links to lots of people. This we've also shown that at the opening event. We asked you while registering what you consider yourself, and so if you take experimentalists and people who consider them both theories and experimentalists together, then it's roughly 50-50. And I think this is what is usually the case at QCrypt. So I think this is not so different from previous years. It's a bit more theory, but together it's about 50-50. And this is also one of the goals of QCrypt, to bring these two communities together. So I think in that sense, we're still managing very well. Then we also asked for this, what your current position is, and we gave basically these options, the first 5, but there was also an open option. So students, I guess that included PhD students or postdoc or faculty member or industry or government. That's what I thought. That's maybe the thing that people can classify themselves in, but apparently not, because there were 9. So you could also add your own option, and so here are all all the things that people actually thought that they the current positions that they hold. There's some interesting ones. A lot of PhDs or PhD students that were not students apparently, but also things like research staff members, alumni, and CEO, banking, finance. I guess I would have thought that's part of industry, but well. So we got a few interesting ones, including self, or quite a few people from the financial sectors as well. So, yeah, I guess we'll put the slides online later on, so you can have another look at this if you're going too fast. Then a bit of finances. So this is a bit difficult to say, and also I cannot say that much at the moment, because we're basically gonna have some mixed finance calculations of this year and next year. But for this year, in particular, the sponsors, those that were already on board, we offered them the opportunity to, at the same price, also sponsor this edition and the next one. So almost all of the sponsors, I think, actually took this opportunity. Not quite, I see. So yeah, most of them did, I think. Plus, we have had some new sponsors that were just sponsoring this year's edition, and of course, we will come back to them and hoping that they will also sponsor the next one. And we offered this year's edition for a much reduced rate, maybe a 1/5 of the price or so, I think, of the original sponsorship packages. And so that gave us an income of about 47,000 euros, plus a generous surplus from last year's edition of QCrypt that was transferred to us. And that's a nice kind of basis we can build on. And expenses for this year were basically not that high. We have hired some services of the UVA, the University of Amsterdam Congress Office, but again, the costs of it are not clearly specified. It will be combined with their efforts on site next year, and they guaranteed us that they will not charge extra for that. So then we had to pay a little bit for this meet and greet room, and furthermore, we did not have many additional costs besides, of course, our own salary and time. So I keep track of my time a little bit, and I've so far spent like about 250 hours on the organization of QCrypt 2020, and I'm sure Serge has a similar number on his site. So that's why we acknowledge all our sponsors, so the gold ones, silver and bronze, plus also the community effort, so our own institutes that pay our salaries. So now this is kind of interesting. So how many people did actually participate so far in QCrypt? So I said 1,000 registrants, but if you look at the viewing numbers of the Zoom participants per session, then this looks like this. So it's a pretty straight line down. And I think, so this is data up to yesterday, but I think today would just continue like this. So it was something like 50 before, and now I think we're at 40 or so. And I think this is a, yeah, we can discuss maybe in the open discussion session actually how comes. So the numbers for those who can see it was close to 300, and so here are 200 and 100. It's just going down with time, pretty much strictly decreasing. So these are the sessions that we had and their starting times. Of course, we have other channels. Well, actually, Zoom. Another thing with Zoom, I found out I can request reports. So Zoom, by you participating in a webinar, actually registers all this of all of you right now. So for every session, I can get an overview of the people who attended, their email, when they registered, when they joined the session, when they left it, so how long they were in there, and from where they connected. So, and then you see some people just coming and going all the time. And from that, I conclude there are some connection problems, at least with some people. Of course, that can be a personal thing, but particularly from China and India, people are frequently reconnecting to these sessions. I guess this is probably due to internet issues. Then, in addition, we have our YouTube channel. So this is some graph from Wednesday. So this is like the duration of the whole stream. And then, of course, in the breaks, there people tune out. But there are roughly like 40 viewers, and the number is the same. At the beginning, there were like 50, 60, then 40, and now 30 or so, also going down. But it roughly looks like this. So those should be added to this Zoom viewing number. So that's kind of people actively participating in the conference. But yet again, they have the stream on. So how active they are, nobody knows. Okay, a quick word about the website. So this is what I spent most of my time on. So far we have been using WordPress for the QCrypt websites. But this year, I've decided to change up things a little bit and learn a new programming language. So it's this Hugo. It's based on Go. It's a static website generator, and it's based on the Jam stack. So I'm just throwing out some words for people who might know. And Jam stands for JavaScript, API, and Markup. And this was actually pretty fun to do. I mean, I learned a lot by making this. The whole thing is open source on the web, so you can go and have a look and see. I'm happy to explain you more how it actually works. And of course, I've not built that myself from scratch, but there are conference website templates out there, and we basically just took that and modified things from there. But that's how it goes in the open source world. And the whole site itself is kind of serverless, so there's no actual server. It's just a content distribution network called Netlify that pushes this Jamstack approach. And they generously gave us an open source plan because we're just doing something good for the community, so we're not paying for their services. But I think it has worked pretty well, and I'm pretty happy with how that went. So if you have a website, you can put on Google Analytics, and then it makes pictures like this. So this is where the users come from. In particular, since the conference has started last weekend until now, this is just user statistics where people are looking at sites, and we see the top countries are, not unsurprisingly, China and the US, followed by the Netherlands, probably partly ourselves, then Germany, UK, Japan, Canada, India, Singapore, Russia, France, South Korea, Switzerland, Israel, Australia, Austria, etc. So again, I'm not very surprised by this list, but it's basically like a who is who of the QCrypt participating countries. And of course, Google Analytics knows much more about the people who are actually visiting this webpage. So to end with, I'd like to thank the team that is enabling all this. There's a bunch of students of our, mine and Serge's group, Jan and Jelle, Alex, Jana, Merdat, Chris, who has been helping out today, Esteban, who has been doing the design, all the sheeps and the bicycles. So thanks a lot to them for helping out, and also the people working at the UVA Congress Bureau and our secretary for making all of this possible. And last but not least, I'd like to thank Serge for his efforts, and he will tell you something soon. And before I leave, I give you some impression of our home offices, which don't look that look quite similar actually. Just hook up as many screens as you can, and then you're ready to run an online conference.
Serge, you are muted.
Thanks. Yes, always forget. So I'm taking over from here. Because I have the pleasure to announce next year's QCrypt. So this is going to be the 11th edition, the 11th conference in this series. And well, it's no surprise, already been mentioned a couple of times that QCrypt 2021 is going to take place, at least that's the plan, then again as a physical conference, at least that's what we're hoping, in Amsterdam, as it was originally planned for this year, but then for known reasons, it's already been addressed, right? We had to switch to an online version around May or so when the decision was made. Now you can also see here that I'm using the slides from last year that I had used at QCrypt 2019 to announce QCrypt 2020 at the time when, well, no one had any idea of what's going to happen this year, and the plan was to have it a QCrypt 2020 here in Amsterdam on site, and I've just very clumsily now, as you can see, adjusted the slides to announce next year's edition. It's still going to be run by Chris and me. Chris just mentioned it's not the two of us alone. We have to have an awesome awesome help from local support staff. So another thing that is still the same is that Amsterdam is still a very exciting city that is worth visiting and has much to offer beyond the conference that hopefully is going to take place here next year. Also, what's still the same is that Amsterdam is easy to reach and easy to get around in. And as it was originally planned for this year, the venue for QCrypt 2021 is going to be the Routers Island campus, which is a modern university complex that features state-of-the-art facilities and is close to the city center. So one thing that is changing is that we won't have any other big event taking place in the same week as QCrypt next year, well, at least as far as we know so far. So this is in contrast to this large sale event that we announced last year, which was supposed to take place in this very week, but then for well-known reasons was then cancelled eventually as well. Now this, on one hand, is a pity that we're not sort of sailing along with sail next year, but there is also an advantage to this, to which I'll get in a minute. Next year, we will hopefully also be able to invite you again for a conference dinner, right? That's sort of something that we couldn't offer this year with the online edition, where exactly it's going to take place. So that's something that is still under discussion. So the positive aspect of not having a QCrypt 2021 along with another huge event taking place in Amsterdam is that this should make it easier to find accommodation as we had sort of originally anticipated for this year's edition. Well, so it's going to be as easy or hard to find accommodation as it is sort of for an average week in the summer in Amsterdam. So these are the things that make up one part of the conference. I mean, the other part, that's your contribution. So your task is going to be for the coming year to come up with new cool results and submit them to QCrypt 2021. And well, with this, I'm concluding. I want to say it's great to have you here for this online conference. But we are very much looking forward to be able to welcoming you in person again for QCrypt 2021 next year in Amsterdam. And with this, I'm handing back to Kyung.
Okay, thank you, Serge and Chris. Now I think we are open to discussion. I notice if you have any question, put it in the Q&A or in the chat. And I noticed that, oh yeah, Dave, you want to say something? Dave?
Hello. Is there any procedure of certification?
Do you want to repeat the question? I don't think anyone understood.
So are you, here's Vadim Makarov, are you asking for like a paper certificate that you have attended the conference? Dev?
Yes, yes, sir. Yes. Is there any procedure of certification for participants?
Sure, we can provide that to you. Send us an email, and we will make a letter for you confirming that you participated.
Yes, participation without a poster presentation, because now I am a PhD student in almost final submission stage. That's why, if possible, not necessary.
Sure, you can send us an email to help desk, and we will help you.
Yes. Okay. Thank you, sir.
Welcome. Vadim, you had a question.
It's a small comment. In addition to China and India, apparently Crimea is blocked in remote.
Yeah. Thank you. Thank you for your comment.
In general, I guess it was a bit of an experiment. Maybe we're happy to hear whether people liked it or whether you think, nah, this was no added value to stick to the webinars. Any good? Please raise your hand if you, as attendee, so we can unmute you. But of course, also the panelists are welcome to speak.
Yeah.
Here's Vadim, can I ask?
Go ahead.
Yes,
sure.
Please.
Has anybody talked to the industrial sponsors whether they are satisfied with the kind of experience they get online? I thought that they get very few visitors this way. Maybe it will be a good alternative to give them some time in the sessions, like for a short speech about what they do. Some other conferences give them 5 minutes of the session.
Yes, I think yes, actually, we discussed it among the steering committee, but eventually we decided that for the industrial session, it's better it's better. I think we still want to see some good idea instead of advertisement. And for this online meeting, I think and since this is online meeting, and the sponsors they sponsor the same amount of money, but for two conference, for the physical one and also for this online one. So in that sense, I think they should be satisfied. Anyway, I can speak for. Of course, I couldn't speak for any sponsor. I can speak for the Jinan Quantum Institute. We are okay with that. So that probably the way. Yeah.
Yeah, I mean,
But yes.
let me add to this. I think it's sort of fair to say that sort of with this meet and greet room where we had the sponsor exhibitions, the breaks, and the poster sessions, well, we were at least hoping for sort of more show-ups in there, that sort of more participants would make use of this possibility that we offer, right? Sort of the idea was to compare to just the Zoom webinars, where as a participant, well, you can listen to the talks and then you can leave again, to somehow simulate sort of the additional value that you have at on-site conferences, that you can meet up with your fellow participants. You can walk by the sponsors or the industry exhibitions, maybe even meet new people. Sort of that's what we tried to simulate. And we knew from the beginning that it's going to be an experiment. And that's also what I told the sponsors, that it's an experiment and we have no clue how it's going to work. Also from the technical side, we had no experience with this platform. And I mean, sort of the longer the week went, sort of the more bugs showed up. So we had sort of refreshed the entire room today. So you may have noticed a bigger font, which was sort of I then sort of included on the way, because that was sort of some feedback that we got. But yeah, sort of bottom line is that it was not as intensively used by the participants as we had hoped for. And we would sort of be curious actually what sort of would be the reason. So we would be happy to get some feedback on this, either now in some discussion or then also with the survey that you will get later on.
Yeah, and similarly with the statistics that I showed, basically the participants in the Zoom webinar of like constant decrease. Of course, this can be due to some general fatigue of the conference. At the beginning, it's exciting, and after a while, it's exhausting. It can also go up again. Maybe the crowd. Having an online conference makes it even easier to choose only the talks that you're interested in. But then again, yeah, maybe if somebody has ideas for incentives, how to make it attractive to actually stay and follow the conference, then that would be interesting to know. One idea I personally had is to charge a registration fee for senior researchers, just not to students. We don't, but it's more like a psychological thing that if you paid for something, of course, maybe your grant is paying, but still, it might actually make it worth more to you, and maybe you might be more committed to actually follow talks. But I'm not sure if that's something we should do.
I mean, personally, I don't think it's the fact that some people might just show up for one talk or two or something like this at an online conference. I don't think it's something that we should actively fight somehow, right? I think it's perfectly okay for people to do this.
Yes.
And if there's a core group of people that show up at everything, and just a much bigger crowd that shows up for the few things that are interested in, I think it's completely normal. I think we should just go with that.
Yeah.
So I don't think charging a fee would be a good thing, actually, because I think it would just block out people that are interested in a few things like this.
Okay. Do we have further questions or comments or suggestion? Anything? Okay. Though I guess that we are all satisfied with all we get. I hope so. Anyway. So and then let's go to the next session, the Best Student Paper Award. Let's see. I've been this one. Okay. This now we have the award ceremony, and then Fred and I will give the theoretical and then experiment paper best paper award. And Fred, go ahead.
Yes, so the first award is going to be for the best student theory paper, and the winner is Jiayu Zhang from Boston University for his paper, Succinct Blind Quantum Computation Using a Random Oracle. So the first contributed talk we saw on Monday. I don't know if Jiayu, you want to unmute yourself and say something? I don't know.
Jiayu, you want to say something? You are muted, actually.
Thank you for everyone.
Well, congratulations.
Thank you.
Okay. The next experimental best student paper award goes to Fabian Boitel from University of Münster. Congratulations to Fabian.
Yeah, thank you very much. And also thanks for this nice online conference. So far, it's been very interesting. So yeah, thank you very much.
Okay. So, okay.
Hopefully we will be able to see you next year in person, and we can actually hand over some award to you in person.
Yeah.
So yeah, I mean, we're going to send you a PDF file of your diploma, but then if we can welcome you next year in Amsterdam, you will get a hard copy of it. And okay, sort of let me commit to that, sort of a small present as well. No clue yet what that's going to be. Yeah, we'll find something.
Yeah, some very good answer than fish. Anyway, see you in Amsterdam then next year, I hope.
Okay, thank you very much. See you there, hopefully.
See ya.
Okay, so is this the end? This marks the end of the business meeting.
Yeah.
We're gonna have a bit of a long break now. Of course, everybody's welcome to go over to the meet and greet room again. And we're gonna end the day with a tutorial by David Avshalom, starting at 4 o'clock Amsterdam time. So this is about 45 minutes from now.